Hello everybody, welcome to this channel. Let's explore physics. In this segment of electricity, we are going to discuss about electrical resistance and resistivity. We observe here the atoms and molecules in the metallic wire hinders the movement of the free electrons. This opposition for the free movement of the electrons is what we call as resistance. Resistance in the material slows down the electrons and controls the flow of current through it. Such substances are called resistors. Too much current can destroy many sensitive electronic components such as LEDs, transistors and integrated circuits. So by connecting a resistor at the input, we limit the current through it and protect it. This shows the significance of resistors in a circuit. Resistance of a conductor as such is defined as a property that resists the flow of electrons in it. It controls the magnitude of the current. The SI unit of resistance is ohm, represented by the Greek letter omega. The man who first discovered electric resistance was a German physicist and mathematician by name George Simon Ohm. As a school teacher, he did his research and formulated a law relating potential difference, current and resistance named after him as Ohm's law. Let's conduct the experiment conducted by Mr. Ohm. The circuit consists of a resistor, the one end of which is connected to the battery. The other end of the battery is connected to the ammeter. Here the digital milliammeter is used. The other end of the milliammeter is connected to another end of the resistor. The voltmeter is connected in parallel across the resistor. The change in the resistance can be observed here by the sliding of the slider. In the similar manner, the change in the voltage can be observed here by the sliding of the slider. Well, let's begin the experiment. At constant resistance, as voltage increases, current increases as well. Then at constant voltage, as resistance increases, current decreases. Again, at constant resistance, as voltage decreases, current also decreases. Obviously, at constant voltage, as resistance decreases, current increases. This picture exhibits the analogy of Ohm's law. Let's note the readings to plot the graph and verify Ohm's law. The circuit consists of a nichrome wire, the one end of which is connected to the negative terminal of the ammeter. The positive end of the ammeter is connected to the positive terminal of the cell. The other end of the nichrome wire is connected to the switch and switched to the negative terminal of the cell. The voltmeter is connected in parallel across the nichrome wire. Initially connecting a single cell, let's note the ammeter and voltmeter reading. Next, to vary the potential difference, connect another cell and note the readings. Repeating the process with the third cell and finally with the fourth cell, ammeter and voltmeter readings are noted. We observe the ratio between V upon I is a constant. This verifies Ohm's law. Since V upon I is a constant ratio, the VI graph is a straight line that passes through the origin of the graph. Ohm's law can also be written as R equals V upon I. Thus, the resistance of a conductor is said to be 1 ohm if the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 ampere. Mathematically, 1 ohm equals 1 volt upon 1 ampere. The other way of writing Ohm's law is I equals V upon R. That is, the current through a resistor is inversely proportional to its resistance. For practical purposes, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate the current without changing the voltage source is called variable resistance, and the device is called rheostat. The resistance can be varied by sliding the slider. The three ways of expressing the relationship between potential difference, current and resistance are V equals Ri, R equals V upon I equals V upon R. Let's study the electrical resistance and hence the current for different components. The circuit consists of 4 cells of 1.5 volt each in series with the ammeter and leaving a gap XY in the circuit. First, place the nichrome wire in the gap XY and plug the key and note the ammeter reading. Say 2 ampere. Next, unplug the key and replace it by a 10 watt bulb. Let the ammeter reading be 1.7 ampere. Again, unplug the key and replace the torch bulb and note the reading. Say 0.5 ampere. We observe here that the current is different for different components. Since certain components offer an easy path for the flow of electric current while others resist the flow as the motion of the electrons are retarded by the attraction of the atoms among which they move. Components are classified as good conductors, resistors, poor conductors and insulators based on the resistance offered by them. Now we are going to study the factors on which the resistance of a conductor depends. The circuit consists of a battery, a plug key, a meter and the different wires for which we are going to study the factors all connected in series. First, place the nichrome wire of length L, plug the key and note the ammeter reading. Say the ammeter reading is 2 ampere. Next, replace the wire by a nichrome wire of same thickness but twice the length and note the reading. Say the reading is 1 ampere. Next, replace it by another nichrome wire of same length L as that of the first wire but thicker wire, that is, it has a larger area of cross section and note the ammeter reading. Say it is 3 ampere. And finally, place a copper wire in place of a nichrome wire of same length L and same thickness as that of the first wire and note the ammeter reading. Say it is 4 ampere. It is observed that the current decreases to 1/2 when the length of the wire is doubled but increases for thicker wire, and change in the current is observed for a wire of different material. As we have observed in the experiment, thinner and longer wire offers more resistance while thicker and shorter wire offers less resistance. Resistance also depends on the material of the conductor. That is, resistance offered for the free flow of electrons is different for different materials. Electrical conductivity of metals is more but decreases as the temperature increases, since the vibrations of the atoms make the passage of electrons more difficult to move. Thus, resistance of a conductor depends directly on its length, inversely on its area of cross section, material of the conductor, and temperature of the conductor. Mathematically, R equals rho L upon A, where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. Resistivity of a conductor is a characteristic property of the material of the conductor, represented by the Greek letter rho. It varies with temperature. The SI unit of resistivity is ohm meter. Metals and alloys have very low resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter, while insulators like rubber and glass have high resistivity of the order of 10 to the power 12 ohm meter to 10 to the power 17 ohm meter. The resistivity of an alloy is generally higher than that of its constituent metals. They do not oxidize readily at high temperatures. Hence, they are commonly used in electrical heating devices like electric iron, induction coil, toasters, etc. Metals having low resistivity are good conductors, hence copper and aluminium are used for electrical transmission lines, while tungsten is exclusively used for filament of electric bulbs. Hope you have understood the concept of resistance and resistivity in electricity.